Hello, thank you for coming. So, we're going to talk about continuous and continuity, what it means for a function to be continuous. So, um, before we've been talking about limits, and the definition of continuity is going to require that we understand limits and what a limit is. So, roughly speaking, a continuous function in a continuous function, small changes in the input produce small changes in the output. So, for a function to be continuous at a point, okay, let's consider a function f of x into space as defined on the open interval a to b. On that interval, it looks like this, let's say. So, for this function to be continuous at some point c in a to b, the open interval in which, or a open interval in which f of x is defined. Well, first, f at c for f of x to be continuous at c, 1, f at c must be defined. So, f at c cannot produce division by 0 or anything like that. The limit as x approaches c of f of x must exist, and the limit as x approaches c of f of x must equal f at c. So, you can see here, all of these are true at c. It's defined at c. The limit as x approaches c from the right and left, they exist. It approaches f at c. Now, when does the limit not exist is the next question. Okay, so first of all, f of x is continuous on the open interval a to b if these three conditions hold for all coordinates c in the open interval a to b, not including a to b. So f of x may be discontinuous at a and or b at the endpoints, but it must not be undefined. But it must be defined for every point within that range. So a limit fails to exist if 1, behavior differs from right to left, and the best example of that is, let's look at a very good example of that is f of x equals the absolute value of x over x. If we graph this, we find that if we're looking at the limit as x approaches 0, the absolute value of x over x, that for x greater than 0, the function looks like this. For x less than 0, the function looks like this. So what we see here, and this is -1, this is 1. What we see here is that the function, if we take the limit, we want to take the limit of the function, so we're approaching approaching 0, right? Let's say we're approaching 0 from the left. We get that the limit as x approaches 0, and we use this minus sign to indicate we're approaching from values less than 0. Absolute value of x over x will equal -1, but if we approach from values greater than 0, the absolute value of x, the limit as x approaches 0, the absolute value of x over x equal +1. So the right and left hand side limits, right, left, are different, therefore the limit does not exist. So you can't approach different values. So, unbounded behavior. A good example of this, as limit as x approaches 0 of 1 over x squared. If we graph this, we get a function that looks like this. We get two vertical asymptotes. We get a vertical asymptote at x equals 0. The limit is infinity. As it approaches infinity, from both the left and right. If you were to put in values getting closer and closer to 0, there's no value that the limit converges to. It just gets larger and larger and larger. Finally, we have oscillatory behavior. And that, so, unbounded, oscillations. As x approaches 0, the sine of x, or of 1 over x, and if we draw this, or graph, if we look at it on a graphing calculator, we see that the function looks like this, something like this. It essentially oscillates as x approaches 0. So there is no number that approaches. If you were to put in a graphing calculator and look at a table of values, you'd see that it would just alternate between -1 and 1 over and over and over again as you approach 0. So we're going to erase this now. So limits fail to exist when either we have unbounded behavior, the limit is the function approaches 0 from values from the left to right, or the function oscillates without end. Okay. So, going back to our discussion of continuity, f at c must be defined. The limit at f at c of f as x approaches c must exist, and that limit must equal f at c. So let's look at the continuity of these functions. F of x equals 1 over x. F of x, g of x, let's use different letters, equals x squared minus 1 over x minus 1. H of x equals x plus 1, x squared plus 1 for x less than or equal to 0, and then x greater than 0, and y equals sine x. So, the first one, fx equals 1 over x. So, domain is, so for 1, 2, 3, 4. Domain for 1 is all non-zero real numbers. at x equals 0, we have a non-removable discontinuity. And the removal ones occur when we can factor out the 0 causing the discontinuous term out of the denominator by dividing into the numerator. So there's a non-removable discontinuity at x equals 0, and it's an infinite discontinuity because it will approach infinity. But other than that, the domain is all real numbers that are not 0. So next, 2. G of x equals x squared minus 1, x minus 1. Domain is all real numbers other than x equals 1. However, this continuity x equals 1 is removable because we can factor x squared minus 1 as x plus 1 times x minus 1 divided by x minus 1, and that'll give us x plus 1. And so g at 1 is 2. Is defined as 2. This is a removable discontinuity. So it is not continuous at x equals 1. It is not continuous at x equals 1 because because it's not defined for that value. But the limit is 2 as x approaches 1. So next one, h of x equals x plus 1 for x less than or equal to 0, and x squared plus 1 for x greater than 0. Now, x plus 1 is continuous for all x, and so is x squared plus 1. So we're not going to have any problems. The only problem we could have is where x equals 0. And we see that x squared plus 1 at x equals 0 is 1, which equals x plus 1 at x equals 0, which means that h of x has domain that is all real numbers. And it is continuous. Everywhere continuous. So y equals sine of x is our last one. Domain of this one is all real numbers. And it is continuous on its domain. So let's erase this. And let's say we'll look at properties of continuity now. So the first property of continuity is that, okay, so first, if b is a real number and f and g are continuous at C, then BF must be continuous at C. Okay, then the following must be continuous at C. So BF, F plus or minus G, FG, and F over G if G at C is not 0. Finally, if, and the final one is the composition of f and g. So f at g of x must also be continuous at C. So now we're going to talk a little bit about infinite limits. Yeah. So, limits at infinity. So, we'll look at infinite limits, and by that we mean that the function does not approach a finite value as x approaches C. So the limit will not exist as x approaches C. And what we'll have is what's called a vertical asymptote. So let's say we have a function f of x, and at x naught the graph looks like this. This x naught is the graph of this should be f of x the graph here of f of x has what's called a vertical asymptote at x naught. So x naught is x equals x naught is a vertical asymptote of f of x. So and as we can see, as f of x approaches, if we were to plug in values that were arbitrarily close to x naught, we would find that as we get closer and closer to x naught, f of x would increase without bound. So let's look at finding these asymptotes. So the first one we'll look at is f of x equals 1 over 2 times x plus 1. then f of x equals x squared plus 1 over x squared minus 1, and f of x is cotangent of x. We'll look at finding the vertical asymptotes for these functions. So first, we see that in the denominator of f of x equals 1 over 2 times x plus 1, at x equals negative 1, the graph, the function will have a 0 in the denominator. So we can conclude that we have a vertical asymptote as if we were to approach x equals negative 1, we would have a undefined, or a limit that would grow without bound. So we can write it that way, the limit definition. So for this one, b, fx equals x squared plus 1 for x squared minus 1. So again, we're looking for asymptotes, vertical asymptotes. So we'll see when the denominator is 0. That will be, after factoring, we see there will be at x equals 1 and x equals negative 1. So we have vertical asymptotes. So this, what we do for this one is that we rewrite, we know that cotangent of x can be written as cosine x over sine x. So with that in mind, what we're going to look for is where sine x equals 0. And in trigonometry, we know sine x equals 0 when x is going to be equal to n times pi. So any multiple of pi. So there are infinitely many vertical asymptotes at all x equals n pi. So x equals pi, 2 pi, okay, and n equals to 1, 2, 3, and so on and so on to infinity. So let's erase this. Let's look at for vertical asymptotes of the function x squared plus 2x minus 8 over x squared minus 4. So again, we're going to factor. The numerator factors to x plus 4 times x minus 2. Denominator x minus 2 times x plus 2, which leaves us with x plus 4 over x plus 2, which means that x equals negative 2 is a vertical asymptote. And if we were to draw the graph, we would see something that kind of looks like this. That's negative 2. What we see is that the limit as x approaches negative 2 from the left, so going this way, it's going to be here, right this way. Limit as x approaches negative 2 from the left of x squared plus 2x minus 8, where x squared minus 4 equals negative infinity, and limit as x approaches 2 from the right, so going this way, of x squared plus 2x minus 8 over x squared minus 4 equals positive infinity. So x equals 2 is not a vertical asymptote. We see that it cancels out of the numerator and denominator. However, the function is still undefined when x equals 2. It's a removable discontinuity. So, and those are infinite limits. Let's say we have a function has here, we'll do it this way. Let's clear the space and we'll say f of x here. Let's say that the limit as x approaches c of f of x is equal to infinity, so it's infinite, and limit will not exist, and the limit as x approaches c of g of x is finite, L. So a few properties. The limit as x approaches c of f of x plus or minus g of x is of course going to be infinity. The product of the limits of the functions f and g, the limit of the product of the functions f and g as x approaches c will be infinity. If L is greater than 0, and will be negative infinity when L is less than 0. And then, final property is that the limit as x approaches c of g of x over f of x must be 0. Because we can see that the denominator will be approaching infinity, while the numerator will just be approaching some constant value. Okay, so that's the video. Next time we will be introducing differentiation, so we'll be getting into real calculus. Thanks for watching. If there's a video on a specific topic that you'd like to see, just let us know in our comment section or go to our website. Bye. Thanks.